Okay, so the way we're going to prove this theorem is we're going to do a proof by contradiction. So we don't need this drawing anymore, we just need our real number line now. A proof by contradiction, so it's going to be proof by contradiction. So I'm going to assume the opposite of what I want to prove. So I'm going to prove that there is not, so this is the set S, and we've got some infinite subset of this point. So you can imagine picking an infinite number of points in this set, and that's your subset T. And what we want to prove is that there exists no point in the closed interval S which is a limit point for this. Okay, and we know that S is compact. So that's our assumption, and we want to show that it leads to a contradiction. Okay, so I'll just write out basically the assumptions. We're going to assume there does not exist, I think you do that with that, does not exist an X which is an element of S such that X is a limit point for T, X is the limit point for T. Okay, and the other assumption we're going to make is that S is compact. We know that, that's a fact. S is compact. And the final thing we know is that T is an infinite subset, and that's going to become important. Okay, so if we know that, if we take our first assumption, then that means that we can take this boundary point on the closed interval of S, so this point here, the camera just blurred, oh no, what's it doing? This point here, and if it's not a limit point, then there exists some ball that we can put around that point such that within that ball there are no points of the set S, of the set T, sorry. So we can draw a tiny little open ball, and it won't be infinitesimal. Make sure you realise that if this is not a limit point, then there will exist some finite real number such that when we take the ball around this point of radius that number, then there exists no point and no element of T that is contained within that ball. Okay, so now what we can do is we can move to this point here that's on the boundary of the ball, and we can say do the same thing. If this is not a limit point for the set T, then there exists a ball that we can put around it. And then we can go to the next point, do the same thing. And we might need, obviously these can be very, very small, so we might actually need an infinite number of balls to go along, but we could eventually go all the way along and cover our entire set. And what we would have proven there is that we wouldn't have proven, you see, what it looks as though we've proven is because in none of these balls there can exist, in none of these open balls in these open balls around these points there are no points of T. So it looks as though we've proven that for any set, if you have an infinite subset, there has to exist a limit point, otherwise the infinite subset doesn't even exist. But of course what we haven't shown is that the points themselves around which these balls are centred aren't the points of T, because the open balls don't include the boundaries, and we set these at the boundaries. So what we have not proven is that there are no points of T in this in these balls, because the points of T could be the centre of the balls. But now we're going to use compactness, because this set of open balls covers the entire set. So what we know from compactness is that there must exist a finite subset of these that also covers the space. So we take our finite subset of these open balls, and that must also cover the set, or also cover the whole set S. And we know that in the sort of outer bit of the ball, so there's the point at the centre, isn't there, here, and then this is the outer bit of the ball, the bits, we've got loads of little points in here on the real line there. And we know that all of these points are not elements of T, because we found a ball of radius such that there were no points of T, because P, and there exists such a ball because P was not a limit point. Okay, so then we took, so what we know is that these points inside are not elements of T. So the only points that can be elements of T are the centre points, but we know because there are a finite number of balls that there are a finite number of centre points, therefore T can only be finite, which is a contradiction because T was an infinite subset. So we've reached a contradiction. So I'm going to outline once again what we've done. We have, we took our larger set S, and within that set we acknowledged that there was some infinite subset of points that was the set T. And what we said is that if no point in S was a limit point for T, which is what we want to try and prove is wrong, and we have proven that it's wrong because we've reached a contradiction, so this assumption cannot have been right, because these two were both the starting conditions, so you can't say they're wrong. The only assumption that we ever made was this one, so this one must be wrong. It cannot fit with these two. So we then said, take the point on the boundary of S, because S is, we're modelling S as this closed bounded interval, and take this point here and find the ball around that point such that there exists no points in T that are within that open ball. And you can do that because P is not a limit point for T, so there must exist some ball of some radius that we can put around it such that there are no points of T in it, otherwise it would be a limit point of T. So we do that and we get this ball, and then we go to the boundary of that ball in here and we say, okay, that point wasn't included in our ball, so we draw another ball around that. And because it's not a limit point, that point can't be a limit point too, because there are no limit points in S. It's a point in S, and we've assumed that there are no points in S that are limit points of T. So there exists a ball around it that contains no points of T, and we do this all for a long, long time, and we cover our entire set, but we could end up with an infinite number of balls. And we know that the outer bit of the ball, this bit here, does not contain any points of T. So the only points that could be are the points on the boundary, which are the points we're using as the centre of the next ball. So the centres of the balls could be points in T. So what we haven't proven is that, because it looks for a while like what we've proven is that for any infinite subset of a set S, there must exist a limit point, and that's not true. It's only if S is compact, and that's because we could have an infinite number of balls, and the centres of the balls could represent the subset T, the infinite subset T. But now we're going to use compactness, which says that we could cover this entire set with just a finite subset of these balls, and since we take our finite subset, so we've got a finite subset here that covers it. I've drawn that because I couldn't obviously draw an infinite subset of balls. We take a finite subset, and all the outer bits cannot be points in T, so only the inner bits can be T, or only the centre points of the balls can be points in T. So we must therefore have a finite, because we've got a finite number of balls, we must have a finite number of centres of balls, therefore the set T must be a finite subset, which is a contradiction since T was an infinite subset. Therefore, we look at our assumptions that we made. The two we want to be true, therefore this one cannot be in line with this one. Therefore, there must exist a limit point for the set T within the for the subset T within the set S, if S is compact.